Hello everyone and welcome back to another video. So today we're going to be solving the CSES problem set question, dice probability. So I personally spent quite a lot of time actually finding the solution to this. And what I want to do in this video is actually kind of show you how I actually ended up getting the solution. So instead of just showing you the final algorithm to find the solution, I'll try to go through a step-by-step procedure which kind of shows you how you can actually end up to getting such a solution. So real quickly, in this question, you're going to be given a dice, which you're going to roll n times, okay? And every throw is going to give you a number between 1 and 6, right? So essentially, you want to find the probability the sum of the outcomes is between A and B, okay? So real quickly, let's say we have an example. So over here, we threw the dice a total of 2 times. And the question is asking us, what is the probability that the sum is either going to be 9 or 10, because those are the lower and upper bounds respectively. So now let's actually break down this question into a smaller part and try to really understand how we can solve this. So let's just start off, with a very basic situation, which is when you have n is equal to 1. So this is going to be our base case. And based on this, we can actually build up our solution to something else. So essentially, you could think of it as a random variable, but we don't really need to complicate it. But essentially, over here, you have xn, and which is going to be the number, the possibilities we can get. So with a specific rule, we could either get a 1, 2, 3, 4, 5, or 6. Now what we want to find is, given a certain rule, how many of each of this is going to be possible, right? So this is going to be the number of xn, and xn is going to be the sum. So at a specific rule, we can only get 1, 1. We can only get 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. This is because we only have one trial. There's n is equal to 1. So now, based on this information, we find the probability of each of them, right? So again, really straightforward. Since there's only one trial, they are all equally possible. So all of them have a probability of 1/6, right? So this is going to be our starting condition. Hopefully you understand how this works. So this is one thing that we want to keep track of. And what I'm going to do is kind of try to display it in a different way. So let's just keep track of this. And now I want to actually show another part of it. So let's say n is equal to 1. I want you to think about what are all of the possible ranges of values we can get. So, well, we could either get the number 1, and the largest we could get is the number 6. Pretty straightforward. So now let's actually look at n is equal to 2. So in this case, the range of values we're going to get is going to be, so essentially, what is the smallest value we can get? So let's say, so we're throwing the dice twice, and the smallest we can get each time is 1. So the smallest value we can get is 1 plus 1, which is 2. And with the same logic, the largest value we can get is going to be 6 plus 6, which is nothing else but 12. So this small condition defines our lower and upper bounds of all of the possible values we have. So this lower bound is always going to be equal to n, and the upper bound is just 6 times n. So this is a small part of information that we are going to use further on for solving the problem. So now we have the values for n is equal to 1. And what I want to do is actually want to show you that you can represent this as a tree-based data structure. So let's see what that looks like, right? So you could have a head node, and each time you have 6 possibilities. So you could either have 1, 2, 3, 4, 5, or 6, right? And each time, so the leaves, what do the leaves represent? We're going to make each of the leaves represent the sum, okay? So each leaf represents a sum, okay? So we're going to use this logic and try to proceed on. So as you can see, the count of 1 is just 1, and the count of 2 is just 1. And based on that, we can get the probability. And another small note on the probability. So what are the total number of possibilities we have for a certain number of trials? So that's very straightforward. So for n is equal to 1, we have 6 possibilities, right? You can see it over here visually. And another way to think of it is this is going to be 6 to the power of n. So when n is equal to 2, you have a total of 36 possibilities that you can get in terms of a sum. 36 possibilities. Now this does not mean 36 unique sums. Now remember, for n is equal to 2, the range of sums we're going to have is from 2 all the way to 12. So this is the range of sums we can get. But within this, we have 36 possibilities, which give us this result of 2, 12, right? Okay, so hopefully that's clear. And now let's move on to a next step. So let's say over here, n is equal to 2. Now, obviously, the number of sums we're going to have is going to be more. Remember, it starts with 2. We can't get 1, right? Because 1 is too small, right? The smallest we can get is 2. So with the same logic I just showed you, we would go all the way. So 6, 7, 8, 9, 10, 11, 12. So 12 is going to be our largest number. So now let's actually try to count each of these, okay? So now before doing that, how many times can we get 2? Well, that's pretty straightforward. That is just going to be the number 1. We can get 2 only one time, which is when we roll 1 and 1. So now we have the number 3. How do we get the number 3? Well, for the number 3, what we could actually do is we can either roll a 1 and then a 2, or we could roll a 2 and then a 1. So we have two possible ways we can get the sum number 3. So now this would have a count of 2, right? So essentially, you could just think of all of these possibilities, but now let's take a situation when we have n is equal to 100, or n is equal to 3 for that fact. Just thinking of the solutions is going to be pretty hard. So essentially, we want to come up with a simpler way to do this, okay? And this is where we can extend this tree that we're kind of drawing. So I'll just take a different color. I think it'll be easier to see. Cool, yeah. So now this 1, essentially, we can further break it down, right? So what we could do is, let's say we already rolled a 1, and now let's say we rolled another 1. That's the basic idea that we're going with. So when you roll another 1, we said the leaf is always equal to the sum. So this would have 2, right? And then we would have 3, assuming we rolled 2, 2 plus 1, 3. And let's say we rolled a 3. Well, we would get 3 plus 1, 4. So I'm pretty sure you understand the logic, right? So let's say, so now the other possible ways are 5 and 6. So you could get, and 7 as well, right? So after getting the number 1, you can roll the number 1, 2, 3, 4, 5, or 6. And these are the sums that you get. So we can actually split this up furthermore for each tree. So I'll just try to draw like a rough picture. So now for this, let's say I roll a 1, I could get 3, I could get 4, I could get 5, 6, 7, all the way up to 8, right? So hopefully you understand this basic kind of thing that I'm drawing over here, right? So let me just continue. Let me just draw 2 more subtrees, and I think it should be clear. So let's say this is a 4, 5, 6, 7, 8, 9. And now for the rest 3, what I'm going to do is I'll just write the range. So over here, we would actually get the numbers from 5 all the way to 10. This would give us the numbers from 6 all the way to 11. And this would give us the numbers from 7 all the way to 12. So now we're going to use this tree to actually get our final answer. So let me just show you real quickly. So now we found out that the number 3 has 2 possibilities. And the simple way to look at that is how many times does the number 3 appear over here? So 1 time over here and 1 time over here. So, well, 3, we have a count of 2. Now the same way for the number 4. 4 appears once here, and once here as well. So now 4 would be 3, okay? So now going on with 5, so 1, 2, 3, 4. So now we see 5 a total of 4 times. And I'll just fill it up for now. So 6, you would see 6 a total of 5 times. And you would see 7 a total of 6 times. But now, when you go to the number 8, so this is a small observation that took me some time to make, but I'll just point it out. So essentially over here, we have the number 2, we have the number 3, 4, 5, 6, and 7, right? So the number 7 was always came from a subtree of 1, right? It always was from that. But now, for the number 8, 8 does not exist in the subtree. In fact, 8 exists over here as well. This one as well, and this one as well. So 1, 2, 3, 4, 5. But it does not come from the first subtree. So that's actually a really important observation, and I'll just try to build up on that later on. So now this 8 occurs 5 times. Now the 9, so just further emphasizing that. So before, we had 3, 4, 5, 6, 7, 8, right? But now 9 does not come from the second subtree. It only comes from these subtrees over here, which is 1, 2, 3, 4. So a total of 4 subtrees. So this has a value of 4. And then 10 becomes 3. So 10 does not come out from here anymore. And with the same logic of 11 2 times. And the number 12 only appears 1 time at the subtree of 6. Okay? So this is one thing that we have to account for our further solution. So now this is n is equal to 2. And for the probability, we would, let's say we want the probability of when xn is equal to 6. Then in that case, that would just be the number of xn at equal to 6, which is, and divided by the total possibilities, which is 6 to the power of n. So in this case, let's say for 6, right? So that would just be 5 divided by 6 squared, which is nothing else but 5 by 36. So this is what we would actually end up outputting, okay? Cool, so we got this part, but now we kind of understood that this entire thing lays on a tree structure, right? And I just want to further build this on, right? So just real quickly, I'm just going to do this one last time. I won't do it fully, but so you can actually build this even more, right? So now this 2, now you would roll the number 1, 2, 3, 4, 5, 6, and the range of values you're going to get, so you would get the number 3, 4, 5, 6, 3, 4, 5, 6, 7, 8. So 3 all the way to the number 8. Over here, you would get the number 4 all the way to the number 9, right? So this would give you the number from 5 to 10. This will give you 6 to 11 and so on. But this is a very important thing that we have to know, right? So 3 to 8. So essentially, when we were doing n is equal to 2, right? So when the tree had a height of 2, in other words, n is equal to 2, we noticed that the number 2, we saw it over here, and that's it, right? But over here, one thing to notice is we see the number 3 over, so let's say we are looking for the number 3. We only see it here. But now let's say we're looking for the number 4. We see the number 4 over here, and we would also see the number 4 over here. So this would have a range of, what do you call it? So this would be 4 all the way, so 4, 5, 6, 7, 8, 9. So 4 all the way to 9, and so on and so forth, right? So essentially, the number 4, we actually look at it 2 times. Okay. Sorry about that. We actually look at the number 4 3 times, right? So even over here, sorry, I forgot to count that, but we're looking at the number 4 3 times, right? So in the previous n is equal to 2, you can only see it in one subtree per se. So this is where we actually go back to the observation that we made earlier, that these values, they're only there in a certain subtree for a certain interval, right? And now I really want to find out what exactly is that interval. So real quickly, I'm just going to go back to n is equal to 2. And let's say I'm looking for the value of number 2. So number 2 only exists here. Then I go to the number 3. So 3 exists here and here. So each time I'm kind of growing by 1. So now the number 4 exists here, here, and here, right? So it exists under 1, 2, and 3, okay? So I care about the count of 1, 2, and 3 as well, right? Now for the number 5, I care about 1. It exists in under 2 as well, under 3 as well, and it also exists under number 4, right? So just, kind of going on with this. Now I have the number 6. So 6 exists here, over here, over here, over here as well, and over here as well. Now the number 7 would exist at 1, at 2, at 3, at 4, at 5, and at 6. So at this point, we've kind of saturated everything, right? Because why is this number 6 important? Well, in very simple words, we have only 6 possibilities at each throw. So now we have gone, so the number 7 can be found at all 6 of these. So now what that means is that the next number, which is the number 8, right? So the number 8 would not be found at the previous one. So essentially, in very simple words, when I throw 2 dice, I can never get the number 8 if one of them is equal to 1, right? So I cannot do 1 plus 7 because, well, the number 7 does not exist on a die. So that means using this subtree, I will never be able to get the answer for the number 8. So now what I do is I only look at the other subtrees that do so, which is the subtree 2, 3, 4, 5, and 6. Now, with the same logic, moving on to the number 9, well, the branch 2 is too small. So now I only look at the values, so let me just at 3, 4, 5, and 6, and so on. So this number 6 is what we're going to be using. So we only care about the 6 previous values. So that's exactly what it's telling us. We only care about the count of the 6 previous values. We don't care about anything after that or before that. So hopefully that does make sense. And now what I want to do is actually put this, so this is essentially the solution, right? You look at the leaf, you get the count, and so on and so forth. But now what I want to do is, how can we actually program this? And this is where we get a dynamic programming approach. So let's say I have n is equal to 1 in the beginning, right? So when n is equal to 1, what are the probabilities I have? Well, it's written right here. I would have 1 for everything. So 1, 2, 3, 4, 5, 6. So essentially, I'm just going to write the values in green as the index per se. So this is n is equal to 1. And this is for the value of 1. This is for the value of 2, for 3, for 4, for 5, and 6. So it's saying that when I throw 1 dice, I can get a count of 6 one time. That's it. Now, if I want the positive probability of this, I would divide it by 6 to the power of n, which is 6 to the power of 1. Now, let's say I want to extend this to n is equal to 2. This is exactly how you do it now. So one thing real quickly that you should remember is what I said is the range of these values. So the smallest value is 2, and the largest value I have is 6 times 2, which is 12, right? So this is the range of values that we have. So this is automatically going to be a 0, all right? That's how we're going to treat it. So we only start off from here. And now what is this value going to be? So the value, the number 2, how could I actually get it? So let's just think of it logically. I can only get the number 2 when I come down from the branch of 1, right? So if the first number I roll is a 1, then the second number I roll has to be a 1. That is the only possible way I can get the number 2, right? So now going with the same logic, let's say the first number I roll is 2. No matter what I roll in the second number, I will not get the number 2, right? So now this is what we do. We only care about the count of the first number. So that is exactly what we count for. So what you do is you go up a level and you only look at the count of the branches you care about. So in this case, we only care about this, so we add that. So that would be 1. Okay, so now we go to the branch 3, right? So over here, I care about the branch 1 and the branch 2 because 3 is there in both of them. So now we take the number of times that appears. So 1 time and 2 times. So we add them up, giving us a value of 2, okay? So now with the same logic over here, we add up these 3 values for 4. So that gives us a value of 3. And then this would give us a value of 4, right? So we add all of these up. Now for 5, we're going to add all of these values up. And now for 6, we add up all of these values, giving us, well, 6, right? So let me just erase this so we have some space. So this is for the number 7, not 6, my bad. So the number 7 appears a total of 6 times based on this, right? So let's just further extend this, right? So now this is where it gets slightly, so this is just going to be all zeros. So this is where it gets slightly weird, right? So essentially, is this also just going to repeat it being 6? No, it's not. Because the number 8 does not exist in the branch 1. So essentially, we only look at the past 6 numbers. So now, what are the past 6 numbers? So this is 1, this is 2, this is 3, this is 4, 5, 6. We don't care about this because that's too small. When we go to the first branch, we do not get the answer. So we look at the past 6 numbers, right? Or if, let's say there's only 4 numbers before it, we only look at the past 4 numbers. But in this case, the past 6 numbers, and this adds up to a sum of 5, okay? So now same way with the number 9, let's go to the past 6 numbers. So we have 1, 2, 3, 4, 5, 6, and that adds up to 4, right? So now the number 10, so let me just get rid of this. So the number 10 is going to have 3. Number 11 is going to have a count of 2. And the number 12 is going to have a count of 1. That's it. So now this is the basic kind of formula that we're going to use to build up to how much ever n we want. So now let's say I want to build n is equal to 3. Okay, so obviously these two are going to be 0 because like I said, the minimum value is going to be n all the way to 6 times n. Okay, so now we start off over here and the formula is going to be we take the past 6 numbers of the level above it. So at n is equal to 2, we take the past 6 numbers. Well, there's only 2 in this case, so this would be 1. So now over here, we would have 2 plus 1, which is 3. Over here, we would have 3 plus 2 plus 1, which is 5, and so on and so forth. So this is how, using this formula, we're going to build out a dynamic programming array. And now let's see how we're going to index this. So real quickly, let's take the same example as, the same values as the example where n is equal to 2 and A is 9 and B is 10. So essentially, we want to find the probability such that xn is greater than or equal to 9 and less than or equal to 10. So this includes the number 9 itself and the number 10 itself. So this is nothing else but 4 plus 3 divided by, what is it going to be? So like I said, 6 to the power of n, which is 36. And this is going to give us 7 by 36. And when you convert this to a decimal, you're going to get the exact same value that's over here, which is 0.19444. Now let's actually try to get into what this looks like in code. And I did use Python for this, so let me just show you what that looks like. Okay, so I'll just quickly explain the code over here. So I'm taking the input here, and then I'm making our dynamic programming area. So what is the length of the largest thing over here going to be? So that's actually going to be 6 times n plus 1. So 6 times n because of the same logic I explained, right? So that's the largest value that we could actually get. And now the plus 1 because, well, range actually goes only until the value, but we want the value itself also, right? So I'm just going to add 1 for that. And we want n of these, right? So the first one is going to be n is equal to 1, n is equal to 2, and so on. So this is going to be our dynamic programming area. So now we fill up the first part. So we know the value of n is equal to 1 beforehand. So what I'm going to do is, go in a small loop for x in range 6 and fill them all with a value of 1 because I already know the value of n is equal to 1. It's just 6 ones in a row. So now that I have this filled, what I'm going to do is I'm actually going to go to the main loop over here. So I'm going to iterate through this from 1 all the way to n. I'm not doing 0 because I already have the value of 0. And now what I'm going to do is I have for I in range x, comma 6 times n plus 1. The same logic as this over here, right? So I'm only going to the last value for that n, right? So for n is equal to 2, I would only go up to the value 12. That's it. So there's that. And now what is this small loop over here? So this essentially what it does is I'm only looking at the past 6 values, okay? So I get the value 1, 2, 3, 4, 5, 6, right? So if I minus j is greater than or equal to 0, then if that's the condition, that means it's good. So real quickly, what does that mean? So let's say I'm over here, and if I minus j is greater than or equal to 0, that means I would add this number 1. But now let's say I go to the next part, which is 2. Well, that's too small, right? It's less than 0, right? I cannot go to an index of a negative index, right? Well, Python technically lets you use a negative index, but that's just going to mess up the entire problem. So I don't want to do that. So essentially, that's why I have the small condition here. And if that is the case, I'm going to add that to the current position, right? And I go up 1 level. That's about it. So that's the basic loop. And yeah, I think the implementation is pretty straightforward. And now finally, you take a sum of all the values. So let's say your lower bound. So you go to first you go to n, right? You're going to take n minus 1 because the first one is 1 and you want to index it, right? And now the range of it is going to be a minus 1 because, well, the 0th index has the value of 1. So it's going to be a minus 1 all the way up to b, right? So you don't want to include b. You just go all the way until that. So you take a sum of all of that. Now you get a count of everything. And now you want to find the probability. And so you divide it by all the possibilities, which is 6 to the power of n. So that's your result. And then I'm just going to format it. So because they only want us to show 6 decimal points, and you print it out, and that's your final answer. So thanks a lot for watching, guys. And I know it's a long video, but I really hope this video did help. So yeah, thanks a lot for watching, and do let me know if you have any questions.